Right. All right. So welcome, everyone. Good morning, good afternoon, or evening, depending on where in the world you're joining us from. My name is Eric Kalachik. I'm director of Boston University's Hariri Institute for Computing. I want to welcome you to the Institute and welcome you to this talk and series, which is co-sponsored by Boston University's Institute for Sustainable Energy. Quick word about the Hariri Institute. Hariri Institute for Computing at BU here is dedicated to leading integrated initiatives in research and technology development, targeting a broad set of disciplines at the nexus of computational and data sciences, with core strengths in cloud computing, security, data privacy, artificial intelligence, as well as a network of over 300 plus research affiliates across a vast spectrum of disciplines. Hariri Institute is positively impacting people everywhere. So about today's agenda, we have asked our featured speaker to prepare a 40-minute presentation roughly, followed by roughly a 15-20-minute Q&A. We're going to ask those who have questions to enter them, please, in the Q&A feature of the Zoom, and all questions will be held till the end for the Q&A portion of the event. So this Distinguished Speakers Series, just to give you a bit of background, brings up-and-coming innovative speakers with bold ideas in computing-enabled and data-driven areas of research to Boston University, whether physically or virtually. These take place once per semester. The series hosts a handful of speakers clustered around a common theme over a 2-week period. Each speaker gives a broadly accessible presentation highlighting the research, followed by a Q&A. Right, so this particular series cluster that we have here is focused around the interface of AI and sustainability. Humanity is facing the defining challenge of learning to prosper within the ecological limits of the planet. AI and machine learning offer powerful new tools that could open new paths for humanity to embrace sustainability. Right, this series brings together leading thinkers at the intersection of sustainability and AI. It's organized by the Hariri Institute's Junior Faculty Fellows, and I'd like to just take a moment to thank the Faculty Fellows for their efforts in organizing this. So the 3 Faculty Fellows who have done the heavy lift of pulling this together were Garrett Johnson, Assistant Professor of Marketing, Eshed Barr, Assistant Professor, Department of Electrical and Computer Engineering, and Scott Hurst, an Assistant Professor in Law here. So the slide I show you here, showing the 3 speakers that are featured in this series. Today we have Claire Monteleoni, who's going to talk on deep unsupervised learning for climate informatics. That'll be followed on the 7th by Aisha Walcott-Bryant, talking on AI's potential for healthcare to mobility in Africa. And finally, we have Francesco Fusonerini, talking on the 9th. He'll talk about the role of artificial intelligence in achieving the sustainable development goals. All of them will be returning then for a panel discussion on the 11th. So please do keep track of all these dates and please join us for as many of these as you can. Then what I want to do is introduce today's host, right? So today's host is Kate Sayenko. Kate is an associate professor of computer science at BU here and a consulting professor for the MIT IBM Watson AI Lab. She leads the Computer Vision and Learning Group at BU and is the co-founder and co-director of the AI Research Initiative here at the Hariri Institute, as well as a member of the Image and Video Computing Research Group. She received a PhD from MIT, did her postdoctoral training at UC Berkeley and Harvard, and her research interests are in the broad area of AI with particular focus on areas such as dataset bias, adaptive ML, learning for image and language understanding, and deep learning. So Kate, it's all yours.
Thank you, Eric, and welcome everyone to today's talk. I'm super excited to introduce Claire Monteleoni. As Eric said, Claire is an associate professor of computer science at the University of Colorado Boulder. She also previously held positions at University of Paris, at George Washington University, at Columbia University, and she got her PhD and master's in computer science at MIT and did postdoctoral training at UC San Diego. And Claire also holds a bachelor's in Earth and Planetary Sciences from Harvard. Claire's research is on machine learning for the study of climate change, helped launch an interdisciplinary field of climate informatics. She founded in 2011, she co-founded the International Conference on Climate Informatics, which started as a workshop and then became a conference, and is turning 12 years old this year. And so this conference has brought together climate scientists and data scientists from lots of countries, over 20 countries all over the world, and many US states. And so that's a really enormous achievement, bringing these folks together. And Claire is also founding editor-in-chief of Environmental Data Science, the journal, and she's also on the Senior Advisory Council for the Workshop for Women in Machine Learning. I've known Claire for a long time. We met at MIT and also through being in machine learning together. Claire's research, is super cool. We'll be hearing about today's intersection of climate informatics, machine learning, but she also works on more core machine learning with sort of learning from data streams, non-stationary data, spatiotemporal data, active semi-supervised learning and unsupervised learning. So lots of other topics in machine learning that are part of her research. So very excited to hand it over to Claire for the talk.
Thank you for the very, very kind introduction, and let me start sharing. Great, so I'll assume I'm in full screen mode unless I hear otherwise. Yes, thank you both for the wonderful invitation back to BU. I've given a talk physically there in the past, so I know it's a great place. Yes, so we study climate informatics due to the threat of climate change and these extreme events we've been seeing, such as megastorms, heat waves resulting in wildfire and drought, and their effects on communities and ecosystems. And climate informatics is based on the vision that machine learning can shed light on climate change. Of course, we know there is a scientific consensus on climate change, but if you ask any climate scientist, they will tell you that there are a lot of remaining uncertain questions. And I opened with those pictures of extreme events. It's actually quite an active area of research to understand how does climate change affect extreme events. And let's look at what is known. This is actually from the 5th assessment report of the IPCC, but as you've probably heard, this summer, the 6th report came out. But even at the time of the 5th, they could tell that since the 1901, we had temperature trends. This is observed temperature averages that were clearly rising worldwide over the period. What's really neat, and I would encourage you to look at these IPCC reports, is that they often have front matter called summary for policymakers. And this one, for example, gives a sense of the remaining uncertainty that we have. So the IPCC put this together as sort of a thought experiment. So imagine if we saw the temperature trend data and we saw that the mean was shifting warmer. Imagine if we started with a probability distribution of temperature that's like this normal, or technically we'd call this a Gaussian distribution. So just a symmetric distribution with some mean, and then the x-axis is temperature. So as we go out in this direction, we're talking about the area under the curve being, the probability of warm events. So if we just have a trend, a mean shift to a warmer average, then we would move to the probability distribution in the dotted line. And what that means is that we would expect higher probability of extreme hot events, but lower probability of extreme cold events. Now, the trend data shows a mean shift to a warmer temperature. So we know that some of the effects that we are seeing are certainly just due to this. But as they notice, this is sort of a very simplifying assumption because it's assuming that from, past in gray to future or present in the dotted line, we've only had a mean shift. But there are other properties of a distribution, like the variance. So even if you had no mean shift, but you just went from the gray distribution to a larger variance, then you have what's called heavier tails. So higher probability of extremes in both directions, higher probability of extreme cold and hot events. And since there's uncertainty about the variability, there's uncertainty about these tails, these extreme values, and to what extent they're being affected by climate change. And as part of this thought experiment, the IPCC sort of wanted folks and policymakers to realize there's actually an infinite number of possibilities of what's going on. I mean, a lot of strong assumptions were made, the shape of the distribution, the fact that it was symmetric. And among the infinite number of possibilities are scenarios with asymmetry, where we might going forward see extreme hot weather increasing without any decrease in the amount of, or the probability of extreme cold weather. So a lot is still unknown. Say we were to approach this using AI, in particular machine learning, where we're trying to, predict how frequent these extreme events would be. Well, in historical data, by definition, extreme events are rare. That means that the instances of them are, less likely than non-extreme, and that's what we call class imbalance. Say we're trying to do classification or prediction between extremes and non-extremes, we'd have severe class imbalance because these events are rare. And then just looking at the temperature variable, we went through that IPCC thought experiment showing that climate change may change the distribution of temperature, and that's going to change, the probability in those tails and those extremes. So it's very hard just from statistics computed on historical data to really reason about what is needed for future prediction on this question around extremes. But this is a really unique domain. So for around 50 years, labs around the world have been getting together to try to model future climates using first principles from physics and mathematical models, so differential equations and coupled systems, so that you could start with some initial conditions, let the model run, and then take the temperature of the Earth in the future in a simulated way, and actually millions of other variables. And these are all evolved over space and time and create large simulations. We can view those simulations, though, as data that the AI can analyze. And of course, machine learning likes the big data playground. And so that's why this is a good domain for us. And just to step back a little bit about the data types available, what I mentioned was this third category of the simulations, the physics-driven simulations called global climate models. This is a very interesting domain because as we go further into the past, we have less and less certainty on any of our measurements because we didn't have all the instrumentation that we have in the present day. So instead of being a big data problem in the past, it's sort of a collection of different types of small data that are spatially rather sparse. Some of them do have a snapshot back in time. So if you look at a very old tree or a coral in the ocean, you can get proxy estimates of temperature and atmospheric concentrations because trees and corals are known to thrive better under certain nutrient conditions and temperatures. The similar types of proxy records are in the cores of sediment below lakes and in the ice cores that have been taken over glaciers. So you've got small data, very heterogeneous. Some of it goes back very far in time and can give us some information. Currently, we're in the observation era. Massive amounts of measurement data sources, from satellite imagery to probes in the ocean using buoys that can sink and rise and measure, and balloons in the atmosphere, and then just local weather measurement stations have created a very dense and highly measured amount of data, but only in the past couple hundred years or so have these really filled in to the point where the data is extremely high dimensional, And now you get into a setting where maybe the information that you need is in a lower dimensional space. And so a lot of more issues come in. In general, it's a great playground, but again, it only goes back to the relatively recent past. So that's another sort of check in favor of climate model simulations, because unlike the other two sources of data, it's the only lens we really have into the distant past or the distant future, albeit simulated. And there are some concerns, for the most part, a lot of domain knowledge and laws of physics are encoded. So this is really nice, good data that helps us. But by the same token, due to constraints on computation power, not everything is directly modeled. For example, clouds cannot be directly modeled because that would require too much compute to model a cloud in the small spatial scale needed and the quick temporal scale that's needed. And then, of course, I said that it's a lens into the past and the future. Well, it can't be validated, right? Unless you had a bit of proxy data, but certainly the future predictions cannot be validated. Okay. So there's critical mass in climate informatics, bringing together climate science and more broadly the study of climate change with all walks of data science, whether you're AI, machine learning, statistics, data mining, et cetera. And as Kate mentioned, we co-founded this conference a while back, and then we added a hackathon. And actually, we did have to skip a year, so we're on our 11th. This is, COVID related, but last year we at least did have a hackathon. And so for those that are available to come to Asheville in May, we're going to be hybrid, so there'll definitely be some in-person activities unless things change. The submission deadline has ended, but it's a great opportunity. I mean, BU has so much amazing climate and sustainability research. I know of several labs, if you're a machine learner, to go across campus and start talking to somebody in domain or vice versa. And then, join our community. And Kate also mentioned this journal, which gives sort of fills in a gap that there wasn't really a venue to do solid machine learning applications to environmental problems without having to try to get rid of the methods into the methods section for the domain papers or focus only on the methods for the ML papers. So this allows people working at the intersection to have a venue, and yes, please submit. So I guess 7 years back now, when Arindam Banerjee and I were speaking at NeurIPS, a machine learning meeting, we were trying to pitch this as, doing for climate change what bioinformatics did for biology. And it was very early days. We were just trying to divide the world into areas that ML was starting to have an impact or might have an impact. So I'll just mention this this as an area of a way to break it into areas, but of course there are many other problems. And as I mentioned, you can find interesting science problems at BU itself. But as I mentioned, the paleoclimate construction, that's a basically very large, sparse matrix over time and space. And how do you reconstruct it to reason about past climates, which are very important in order to predict future climates. My lab has been contributing in the green font. Of course, today, I won't go over all of that. I might have time to talk about the downscaling work, which is how you go from model scale predictions, which are rather coarse, to the fine-grained questions that governments are starting to ask climate scientists. What's the temperature or precipitation going to be in a particular postal code, or even in your own backyard? We've done a whole line of work on taking those climate models, which are each sort of discretizing the clouds differently, et cetera, and try to make an ensemble that has a more robust prediction than any individual model. Like the IPCC ensemble currently is contributed to by around 35 models from all different countries, and they don't actually agree on future predictions. So can we use AI to help combine them? What you will hear about a little today is our work on extreme events, going back to those pictures for the beginning, and then more broadly, if you're interested in spatiotemporal data, that has long-range dependencies, nonlinear interactions, and non-stationarity over both space and time, then this is a great domain. So I'll just outline quickly, because I mentioned that we did a lot around looking at a climate model. So a climate model has to model atmosphere, ocean, land, and cryosphere and their coupling. And different teams have done it differently from different countries. And so the IPCC model ensemble had a lot of disagreement into the future. So as I mentioned, we developed these algorithms for actually learning in a iterative fashion, online learning, from data that is non-stationary over both space and time, which actually opened up a new domain in ML. And we recently provided the theory, the regret framework for that setting. We've also been really interested in the El Nino Southern Oscillation because it, other than the climate warming trend, ENSO, as it's called, has sort of more effect on observable of like temperature and precipitation observations in the whole world than any other factor. But it's not that predictable. It doesn't come every 5 years, or sometimes it could take 9 years or 2 years. And in addition, it might be affected by climate change. So we did causal studies to look at how an index in the Pacific Ocean, the region for that index might be changing. And then we're currently tasked by NASA to look at the altimetry of real sea level rise and use the modeled sea level rise to try to reason about regional and global sea level rise in the future. What I'm going to primarily talk about today falls within our work on extremes. I started with those pictures. On the left is a picture of a storm track forecasting problem where we had track data, so XY coordinates every 6 hours of all these past cyclones and hurricanes in this wonderful NOAA database. And my postdoc registered images, and I'm calling them images, but these are actually just fields of wind and pressure centered around the storm location. And then we were able to actually, just using supervised convolutional neural networks, basically compete with state-of-the-art forecasting at 6 to 24-hour leads of the hurricane location, compete with the National Hurricane Center. And then we're also working with the Indian Meteorological Department around the precipitation extremes from the monsoon in India, which we know has a great effect on the GDP of that whole subcontinent. But the case study that I'm going to talk about today is about avalanche detection and the value of unsupervised learning in that. So first we tried with the CNN, which is supervised, and then I'm going to talk more about the unsupervised approach. And I was on sabbatical in France, so this was done with Météo France, which is basically NOAA in France. And sometimes I try to give the take-home messages earlier in the talk. Where I'd really like our extremes research to go is to look at cascading hazards. Actually, recently nearby where I live, we had this cascade of very extraordinary events. So in the most recent fall and winter, we didn't get any snow, which is anomalous for our region, and it made the vegetation very, very anomalously dry. Then there was a day with anomalously high winds. So all it took was a single ignition, it's believed, and then this uncontrollable wind-driven firestorm just attacked all these suburban areas. It was not really a wildfire. It was not out in the wild. It was just burning homes in suburbia. A lot of animals' lives were lost. Luckily, it seems like only 2 human lives were lost, but the number of homes damaged, the number of homes completely leveled was over 1,000, and there's hundreds more damaged, and it's had a major impact on the region. You can also get these combined more wet events. So in Santa Barbara County, a few years back, there was a wildfire in a mountainous region that already destroyed over 1,000 structures and had air quality degradation. But because of past drought, when an intense rainfall fell on the fire scar. Actually, the fire was still going, but in some areas it was, just earth that was pushed with these massive waters in what's called a debris flow. I wish we had a stronger term for that than a debris flow or a landslide. We're talking boulders coming into your living room, and there was significant loss of life. So what we have to do eventually is reason using AI about when these extremes cascade together into these mega extremes. But we're going to just start with single extremes. And for the focus of today, I also wanted to give a little taste around methods. So I decided to focus on the power of unsupervised deep learning. Probably I'm only going to have time to talk about our avalanche detection work, and that falls under extremes, but if time, maybe I'll talk about downscaling. So for avalanche detection, we are ultimately, since it's a detection problem, there has to be a wrapper that's supervised learning, right? We want to be able to say, here's an avalanche deposit and here there isn't. But what we are arguing is that your semi-supervised pipeline should lean as heavily as possible on the unsupervised learning aspect. And this was led by my current student and my former postdoc, whose hurricane work I also discussed and came out in the 2020 climate informatics. There does seem to be increasing safety issues around avalanche, and avalanches may be increasing with climate change. And then for the machine learners in the audience, we can think of this as a problem with class imbalance, right? We're trying to do anomaly detection for very rare events. And in this particular application, it is also a problem with just some fixed small amount of labeled data, meaning there had been a ground truth survey and we know where the avalanche deposits fell and didn't fall, but just on really a subset of the data. This was actually ground truth measurements. Trekkers had to go into certain avalanche corridors in the French Alps and see if there were avalanche deposits. And so that's the ground truth survey provided by Météo France. And then we had, the unlabeled data was the satellite imagery, in particular synthetic aperture radiation imagery. So you can kind of think of, you have as much unlabeled satellite imagery as you want, but you have just some very limited amount of labeled data. And just to distinguish, you could imagine some in-between version where Météo France could give us SAR imagery that had been segmented and labeled as to which regions had avalanche by experts. But they were having trouble even training human experts because you're just looking essentially at SAR imagery of snow, and there's some minor textural differences. It's very hard to tell where there's an avalanche deposit for the human eye, at least at that time. So that's all we had was ground truth from the ground and as much satellite imagery as we had. So here's a first idea just to gain intuition on the pipeline. This is an anomaly detection event because avalanche is rare. So you could do unsupervised learning, and I'm going to explain the VAE in a second, but you could just get a model of negative examples of image patches that don't have avalanche in them. So that way you could have sort of a wrapper around that to classify an unknown image as anomalous or not. Basically, is it similar to the data that you trained your model on, which were the negative examples? Now, of course, you're going to need to tune this threshold, and that would take labeled data because that's a hyperparameter used in the supervised learning part. But you might notice that there has to be this step 1.5 that we view as the bottleneck of data labeling, because you have to use some of that precious ground truth survey to sort out the patches of satellite imagery that corresponded to actual avalanche deposits in order to give me patches that do not. So we'd like to do away with that step altogether and use our labeled data only for this thresholding task. And so that's exactly what we do. So we'll just replace step 2 with training an unsupervised model. We don't know whether the patches have Avalanche in them or not. So now I'll just quickly do a technical slide. I realize people are coming from all different departments across campus, and I'm not supposed to get too technical. So you can just relax for a second, check email if this does not make sense to you. But for the people that are familiar with supervised deep learning, I just want to make a point of really how simple it is to extend from supervised to unsupervised deep learning. And the point is as follows. Whatever your architecture is, let's just call your network acting on an input example as F sub W, and W are the parameters of your network. So your network has some architecture, and then you've got these weight matrices going between different hidden layers. Let's just throw all those parameters into W, and then we'll denote our output of the network as Y hat. Well, supervised deep learning means that in addition to your input, which is like your image of SAR data, or it could be a vector tensor, right? In addition to your input data, you have the desired ground truth label for that, meaning in this case, is it avalanche or no avalanche? So, you know, and then that's your loss function or your objective function that you're trying to minimize. And then what is all of deep learning? Well, it's just taking, you know, messy or noisy gradient descent steps on this objective. And when you take one step, you can propagate back using the chain rule for taking derivatives of how every little parameter in this whole set W will update. Fine. So that's simplifying all of deep learning. What's the difference in the supervised case? What's the difference in the unsupervised case? Well, you don't necessarily have a label, but I still, even if you don't have a label, want to empower you to potentially use deep learning, which is that you just want to define now an objective function or a loss function that's not allowed to depend on some, you know, ground truth label Y. So it could certainly depend on the input to the network in addition to the output of the network. Nothing really has changed here. I have some architecture. I've got some parameters W that I'm going to estimate from data, again, by doing gradient descent on this objective function, and then propagating the updates at each layer using the chain rule. But what would this mean? And as a sidebar, there's been a really interesting field around deep clustering, where, you know, we know clustering objectives depend on the whole training data set, but you could also do variants of them that only depend on a mini batch. And there, so you're only looking at the input and the output. And there's this paper, I don't know if it's the real title, but the subtitle is Spectral Clustering Without the Spectral Clustering, where you can write down the objective for spectral clustering and then just use a deep learning to optimize it. So that's pretty neat. Today we'll be talking about more a loss function that you might do to just pull the input image to be close to the output image, which seems like kind of silly. But the point now is for dimensionality reduction. So what do I mean by that? So a standard autoencoder is a very dumb machine that nobody needs. Nobody needs a machine that is basically just a noisy version of the identity function. So the input is like humans drawing digits on a grayscale over here. And the machine, once trained, is going to give you almost the identity function, but actually a little worse. You know, nobody needs that, but that's a pretext task. By training the weights that are all in this region, at the end of learning this silly machine, we have now some sort of representation because we've pushed through the bottleneck. We've pushed all the images in the distribution through, and so the weights at the bottleneck we could view as like a reduced feature representation of the data. And so more generally, that's what people mean when they say autoencoder. And if we're doing feature extraction, typically, yes, we're going to go from a higher dimensional space that the images live in to something lower dimensional. I will also just sidebar again that if you go across campus and talk to the neuroscientists and some like human vision researchers, cognitive scientists, there's some evidence that in cognitive systems, we're doing an overcomplete representation. So we're doing a wide layer here. So instead of a bottleneck, we go through a wider dimension, and now we're encoding images in a higher dimensional space than they live. but that allows us to get very sparse encodings, sparse representations of signals that we want to keep separate in our cognition. But anyway, for today, we're going to do dimensionality reduction. And if you're bothered by just having a single representation here, well, you could also learn a distribution of representations. And the simplest way is, learn a Gaussian. So you're also learning the parameters of the Gaussian or the normal distribution while you're, so you'll learn a distribution over this compressed space. And then I probably am not going to have time to get to normalizing flows, but that's a technique that allows you to start maybe with a Gaussian, but then complicate your distribution until it's more informative. But so let's stick with this VAE, this distributional version of the autoencoder, and let me re-explain those pipelines in the context of training a VAE, which is this whole region here. So the strawman version that I proposed was that you would train it only on negative examples. So you'd have a model of what a non-avalanche patch looks like. But I mentioned there's this bottleneck at the beginning where I have to look at the ground truth survey, I have to look at the images and label patches as having an avalanche or not. And now I've wasted some of that precious ground truth data collected by those human trekkers. And so we said, instead, let's actually just completely train the autoencoder unawares of whether the images have avalanches in them or not. So just on any image patch from the data. So we say all here, we'll obviously have to save some for our validation data set, but most images without checking what's in them. So you've done one or the other here. And then how do you tune this threshold? Because this wrapper is that you have to classify avalanche or no avalanche. Well, that's just hyperparameter tuning done on a labeled validation set, meaning image patches where I've checked the ground truth survey to see if there were avalanche or not. The autoencoder has already been trained. So I'll pass images through and then compute how similar is the output to the input that will be quantified by the reconstruction error. And then this free parameter here, the threshold, I'll get to tweak until, most of the examples labeled 1 are greater than the threshold on reconstruction error and vice versa. So I need to tune a hyperparameter because ultimately I'm making a supervised, I'm making a designation, a classification. And then once trained and parameter tuned, how is this used? Well, for new data where we don't have the label, we pass it through the trained autoencoder, and then we compare the reconstruction, how similar is this to the data that it was trained on, to the threshold to say anomaly or no anomaly. And in this application, avalanches were the anomaly. It's just snow images and then the texture of avalanche deposits or not. So we can compare this to what Météo France was using at the time that they approached us, which was not AI. It was some deterministic function you can take by thresholding variables available to you in the SAR signal. So just thresholding. And they didn't think that this was doing very well because you would get little teensy avalanches in the middle of a ski town. It was not looking for like connected regions very well. But in general, it's extremely hard to have skill. You'll see these accuracies, hovering around 60%. And we said it was hard even for a human. The baseline was a thresholding technique. Then we did do a CNN version, a supervised version, but then we had to artificially balance our data set, which meant we had a lot less labeled data. And so we got a lift from previous approaches using both of our pipelines. And I should clarify, both of our pipelines are ultimately semi-supervised, but whether the VAE was learned on only negative data or all the data is what we indicate here. And so using all the data, we actually can get a significant lift than only using the negative data. So this at first might seem counterintuitive, but keep in mind that just like in any AI or machine learning paper that you open, when algorithms are compared, they each have their hyperparameters tuned independently, but on the same validation data set. So ultimately, the threshold on classifying an avalanche may turn out different, probably will turn out different when your VAE is just trained on any old data, not just negative examples. But because it's kind of explored sort of more of the feature space, we get, better generalization, less overfitting. And this result kind of persists if you look at ROC curves comparing true and false positive rates with the fully unsupervised VAE training, then in the semi-supervised pipeline outperforming all the other methods. So yeah, we hope this idea, this sort of twist, is interesting and helpful in other domains where you not only have severe class imbalance because you're looking for rare events, but you also have just some fixed, non-negotiable, small amount of labeled data. This can also be viewed as a form of a virtual sensor. Instead of having humans risk their lives in these avalanche corridors and being the sort of visual sensors for avalanche deposit, by learning this mapping from satellite data, we don't have to, hopefully, we can generalize to regions that they didn't explore. And this is more generally a topic that you'll see a lot in AI for climate domains. So NOAA knows that radar is expensive and we only have radar coverage in certain areas. So could we combine this with satellite signal to again use machine learning to map and sort of predict fake radar signal where we don't have it? And as I mentioned, this is all towards building up to actually being able to, this was just avalanche detection. How do we actually forecast? We did do forecasting in some of our other applications, and I'd like to get to forecasting cascading hazards. And I'm just going to be mindful of time, and I think I'm going to skip this downscaling work. Only to say, though, that if you got frustrated at the point of a VAE, now there's this idea called normalizing flow, where you might start with a Gaussian assumption, but then compose a bunch of bijections to eventually complicate your distribution. By using bijections, you can do all your probabilistic reasoning in the space of the priors, which are generally nice and simple. And then you learn the parameters of this composed function, and then you get these invertible mappings. And so kind of the punchline of this work was that we were able to downscale from very coarse resolution to fine resolution, and actually vice versa, because the methods are completely symmetric using normalizing flows. And then you can do things like, let's explore the latent space by taking real images on the far ends, mapping them to the learned feature representation, actually a distribution over the learned feature representation, and taking a walk over that distribution. There's questions now in ML, how best to do that. Can we walk a geodesic on the distribution, or is that too complex? And then output both actually high resolution samples or fine resolution samples and coarse resolution samples to give a domain expert a sense of what the model has learned of how you would do temporal interpolation of either a coarse grained or a fine grained precipitation map. And actually, we're going to use that kind of technique in this new project recently funded by CCAI and the Future Earth philanthropy to downscale climate model data for renewable energy planning in the US and India. Because as we saw, it allows us to go from coarse resolution to fine resolution. And this is a domain, I'm also more interested in how do we work on AI for greening industries, including energy. One thing we've been doing is trying to make solar and wind sources more trustable for grid operators by just reducing the variance on our short-term predictions of them, and also longer-term predictions out to 2 weeks in order to do longer-term planning and resource allocation. So I guess I'll just close with a discussion on sort of open challenges and progress. So some of the limitations of data is that you might not have enough labeled data. We've seen how you can then maybe do unsupervised learning or dimensionality reduction and, dealing with class imbalance in the ways that we talked about. More generally, though, we don't have a counterfactual Earth, right? We just have the time series that we've observed back to a certain point in time. And we can't really experiment with very different climate interventions because we can only, see what has happened. So we're not going to have enough data diversity on the time dimension. But increasingly, and if you look also at some, private products, for example, at Google and some of these commercial hyperspectral satellite companies, we're starting to get extremely high granularity over space, over location. So could we kind of use that as a proxy where we don't have the time, the diversity over time, but we do know different locations, different countries and regions have been doing different interventions. And so we can kind of use spatial diversity to train our models as to the differences of different interventions. One thing that, other than downscaling, that I briefly touched on, I didn't talk too much about is ML or climate modelers are looking for ML approaches to the problem that not everything is resolved at scale. Clouds are going to be really the key to understanding how our atmosphere evolves and what kind of conditions humans are going to face. But they're not in the global climate models. So are there multi-resolution or like kernel regression techniques that can somehow be used? And a climate modeler would call that a climate model parameterization problem. Of course, that word is now overloaded when we think about ML or even just computer science. A huge thrust of our lab worked on worked on non-stationarity. I haven't talked about that at all, but if you're interested, we have these online learning methods that can change, change their concepts adaptively over both space and time. And then interpretability. A whole AI institute got funded around trustworthy AI in this domain. I would have you go check out their website. And then on our end, we're interested in, okay, so now we can sample from these generative models that are learned in an unsupervised fashion. How can we even have confidence that the distributions learned are faithful to the distributions in reality? And then this gets philosophical. If we had a model for the real distribution, we'd be done. We wouldn't even be using AI. So the questions such as those around interpretability of generative models, if you look at something like GANs, one of the best recent works I know of in theory just proves that the generative adversarial network is not memorizing its training data. That's the minimum thing we would hope, but actually characterizing the distribution is still quite an active area of research. So with that, thank you so much for your time, and thank you to my group and collaborators on some of the works discussed.
Thank you so much for a wonderful talk, Claire, and I'll be the proxy for applause that you would hear if this weren't virtual. So at this point, I will ask folks to put questions in the Q&A using the Q&A button. And I see questions already coming in. So, so the first one is from Garrett Johnson, who's asking, how do you think the avalanche results from France would generalize to other parts of the world? In other words, is the model learning something fundamental about how avalanche snow looks that is generalizable? Which is actually a great question. I had that question as well.
I think so. It's actually funny because I'm here in Boulder at the foothills of the Rockies, and for a couple of years was trying to find like who are the researchers I can get the Colorado data from. I mean, we're constantly hearing updates from the Colorado Avalanche Information Center on warnings. It's not something that we've we've tried. So I can't say for sure, but I think it would be generalizable since we're just looking at SAR of these quarters. Now, the structures are different. You know, the Alps are kind of more steep. Here we're at very high altitude, but the mountains are kind of more rolling and round. That's going to affect the angles and other issues affecting how the SAR is measured. So yeah, I don't have an empirical answer for you, but it did. I mean, there's no reason that it shouldn't be fundamental. So I'll, you know, feel free to, if you have avalanche data, send it our way, or maybe we could collaborate and you could apply our algorithm. Interesting point.
Thank you. Another question from Piotr, who says, thanks for the talk. I had a big picture question about ML for climate modeling. It seems like the problem with current models is that the resolution of the models. As compute gets bigger, we can maybe solve more challenging differential equations though. Where does that leave ML for climate?
Great question. So I spent November and December in Santa Barbara at the Kavli Institute for Theoretical Physics, where we hosted this long program where researchers could come in and out on machine learning for the physics of climate. And so I was exposed to a lot of modelers, especially around ocean and atmosphere. There's one cryosphere guy. And yeah, the way they see the space, okay, so they do buy our idea that ML in general can help with dimensionality reduction. And so they had a whole topic on dimensionality reduction, but the rest of how they kind of split up the world was about emulators and parameterization. And by the way, all the talks are online. If you go to KITP and look for that particular long program, that there's just some amazing talks over the 7 weeks. Parameterization is what I tried to get at around the clouds, more generally moist processes that need fine-grained spatial and temporal resolution are not being fully resolved. And then the other one is around emulators. So I see your point that if we had better compute, we could solve the differential equations at smaller scale. But ask any climate modeler, especially somebody who does ice, but also even in the atmosphere and ocean, there are some parts of the system where the physics is still unknown. So it's not just a question of running a differential equation, it's a question of emulating a mathematical model where you don't know the physics for it. There's been some super interesting work. Julien Bragard, who's at Sorbonne and also now is like in this lab, climate lab in Bergen, Norway, has done very interesting stuff around, you know, his application domain was on oceanography, maybe data assimilation for biological oceanography. And he had a pretty simple system compared to a global climate model, which has so many different non-stochastic partial differential equations. But he had a small system with a few differential equations interacting. But then one part of the system was just not known. The biology and physics did not have a good model for it. And so learning these hybrid models where you can emulate using machine learning the parts that have not been parameterized or modeled yet. So anyway, if you want to know where does that leave ML for climate, you know, hot off the presses, that workshop ended December 17th. Go to the KITP website.
Great. We'll have to check that out. So we have another question from Suchi, who's asking, what is your experience in doing ML work integrating across spatial scales? We have continuous coverage on global scales and less on local scales. You spoke of downscaling. Can you elaborate?
Well, I like the point about integrating across spatial scales and the domain experts, so people doing climate change related research, at least on the geophysical and like climate modeling side are very interested in this. And I did do downscaling work to get from a coarse scale to a fine scale, but I think you're talking even about more scales. And I know actually there are like now whole workshops in ML on this. I think like ROC Condor works on that. But what I meant here was that, and thank you for giving me the opportunity to talk a little bit more, is that we had, well, we did our temperature and precipitation studies separately, but we had coarse grain data and fine grain data. And in this case, actually, the coarser grain was more from observations. It was observations run through data assimilation to get reanalysis data. And the fine grained actually was from models. It was from NWP, numerical weather prediction, which resolves at smaller scale. But our metric was symmetric. So we both did downscaling and upscaling. And we did domain alignment. So if you look at recent machine learning work, this is a problem where you want to have IID access to two random variables and then learn a bijection that will allow you to approximate the marginal of one from samples of the marginal of the other, and vice versa via its inverse. So we said that, okay, coarse grained data will be, you know, our one random variable, fine grained data will be our other random variable. And then we used this technique called a Lineflow, which came out in the 2020 AAAI, which was just sort of interesting because ideally you want mappings between low resolution and high resolution, ideally like invertible probabilistic mappings. And so ideally you want like this joint density. And so if you assume the presence of a latent space that you're going to learn a posterior over, and then also assume that your two domains are conditionally independent given the latent space, then of course that's a way to compute the joint. And then these conditional distributions of, you know, the coarse resolution data conditioned on the latent representation domain, and similarly for the fine, those are learned using normalizing flows, where you start with some prior and get a mapping from one space to the other. And so the technique was this, I mean, it looks complicated, but it's this nice technique out of AAAI where you're just learning the parameters for a flow that maps from the low resolution data to the latent variable, and another flow where you'll learn its parameters from the high resolution data to the latent variable. And yeah, that was that technique. It's super general. We did proofs of concept on temperature and precipitation, but I think that technique does have a lot of promise. But in terms of multiple scales, there are interesting techniques. For example, like the whole idea of kriging, which came out of geospatial statistics, is that, you know, you'll have signal at a whole variety of spatial scales, and how do you like integrate to get, you know, point estimates, etc. And in general, yes, we do have to deal with multi-scale. Like on a day-to-day, you have the daily scale, say, of temperature, seasonal and annual, but then there are these climate modes of variability. El Nino Southern Oscillation just being one. There's, you know, North Atlantic Oscillation, Madden-Julian. There are all these other oscillations that have timescales of multiple years and also can be variable. So I don't know, you know, Suchi, if you're coming more from ML or from the domain, but integrating across spatial scales, if you have ML methods for that, you would find great interest in the modeling community, or even in the climate change research community.
Great. I wonder if we have time for one last question. Okay, great. So one last question. This is from Adam, who says,
Hi,
thank
Adam.
you for the talk. About interpretation, I guess interpretability, what sorts of specific challenges arise with climate models? What are the scientific and physical insights one might hope to gain out of trained models?
Okay, well, the second question, Sanjay Dasgupta and Kamalika Chowdhury, I believe, or at least Dasgupta, had a result on a test that you're not memorizing the training data. And that at the time I looked, that was like the best thing you could show about a GAN. But in my backup slides, I will quickly answer your question. What are the insights you can gain out of trained models? So one of the most famous ones are about causal attribution. Models can be run for the future, right? And that's very important if we want to say, okay, what happens if we turn off emissions or we have the same emissions? Those are important to analyze future scenarios. And a lot of those future scenarios are being simulated by modelers. And I claim that it's so much data, we need AI to analyze it. Right, but when you ask about the trained, the trained models, the ML models, or the climate models?
I guess, well, if I had to interpret that, I don't know if Adam can speak up, but I would interpret that as you train the ML model on some climate data, and then you want to interpret essentially what it learned.
Yeah, so let's see. Yeah, so this work that I skipped over, we can uncover spatial neighborhood dependencies, temporal dependencies, like if the NASA model is good at predicting from January to May, then we can test the hypothesis that it's also good at April and June. We can also look at the time series of weights that the ML model provides to the climate models and say, hey, you know, the NCAR model is not performing as well as Max Planck during a La Nina event or something like that. We can actually do machine learning, matching our findings to known underlying physical processes. We have not done that. But this, when you ask about specific challenges, I mean, you know, just the challenge right now is that they're not really agreeing into the future. I mean, even under like a scenario like this, the ensemble spread is indicated by these different colors. So an ensemble from a lot of different countries, you know, different models are kind of giving us different worst case scenarios.
Very cool. Well, I think with that, we'll end this session. Let's thank Claire again very much for coming and for the wonderful talk. And
Thank you.
We'll see you at the panel.
Oh yeah, see you next Friday. Thanks.
Yeah, so bring more questions.
Oh yeah, I'll be here next Friday at this time. Thank you.